Welcome to Theory of Computation. This is lecture number 11. In the last lecture, we looked at the undecidability of the halting problem. We noticed that the halting problem is the central undecidable question. That is, the first question that we proved was undecidable. After that, we looked at several problems concerning Turing machines. We looked at the acceptance problem for Turing machines, which is the halting problem. Then we looked at the emptiness problem, the equality problem, and so on and so forth. And we proved that all these problems were also undecidable. We also looked at Russell's paradox and related problems and saw how the central argument from Russell's paradox is used to prove that the halting problem is undecidable. Today we would look at other problems concerning other machines. So for example, we would look at linear bounded automata and context-free grammars, and I try to identify decidable and undecidable questions about these machines or these models of computation. Remember that for us to prove that the halting problem was undecidable, we had to come up with an ingenious argument. That argument was given first by Alan Turing. He showed that the halting problem was undecidable. Once we have established the undecidability of the halting problem, we can use that fact to prove that other problems are also undecidable. For example, we proved that the emptiness problem for Turing machines was also undecidable. And the proof went as follows. We assumed that the emptiness problem for Turing machines is decidable, and then we said that if it is decidable, there is a decider for it. There's an algorithm that solves that problem, or there's a Turing machine that solves that problem. We took that decider and used it to construct another decider, and then we showed that that other decider was actually deciding ATM. However, this shows that if the emptiness problem is decidable, then the acceptance problem or the halting problem for Turing machine is also decidable. Since we already know that ATM is undecidable, therefore the emptiness problem must also be undecidable. This was the main theme. We start with a problem which we want to show is undecidable. We assume that it's decidable. This gives us a decider for that problem. Then we try to use that decider to come up with a new decider which will decide ATM. If we are able to do that, we can conclude that our original problem must be undecidable. This argument at the heart is what we are going to call reducibility. Reducibility argument goes as follows. I know that ATM is undecidable. If I can take a particular problem and show that the ATM reduces to it, that if I were given a solution for my problem P, I could use it to find a decider for ATM, then I can conclude that this problem P is also undecidable, since I know that ATM is undecidable. The outline of today's lecture is going to be as follows. Today we would look at a new model of computation called linear bounded automata. After that, we would look at the acceptance problem for linear bounded automatas, and we will show that this question is decidable. This question is easier than the acceptance problem for Turing machines. Then we'll look at the emptiness problem for linear bounded automata, and we will show that this problem is undecidable. In order to do that, we will develop a new technique which is going to be based on computation histories. After that, we would look at the emptiness problem for context-free grammars. We would just briefly argue that this problem is decidable. So the emptiness problem for context-free grammars is easier than the emptiness problem for linear bounded automata. After that, we would describe an undecidable problem for context-free grammars. And in order to prove that this problem is undecidable, we'll once again use the technique based on computation histories. In the end, we will briefly discuss the post-correspondence problem. The post-correspondence problem is an extremely interesting problem. It is a puzzle, and the solution to this puzzle is undecidable. There is no algorithm that can tell us whether the post-correspondence problem which gives us a puzzle has a solution or not. That we will discuss at the end of the lecture. So let us start. Let's start with the model of computation that we call linear bounded automata. Linear bounded automata is going to be a Turing machine with a restriction. Its head is never allowed to leave the input portion of the tape. So you take a linear bounded automata and you give it an input. The tape head is never allowed to move off the original input that was given to it. So it can only use restricted space, as much space as was taken by the input. So a linear bounded automata uses space which is linear in the size of its input. In fact, it only uses the portion of the tape that was given to it, that on which the input was given. Let's look at a picture of a linear bounded automata. As you can see in this picture, it looks like a Turing machine, except for we have shown that there is input and there is no tape after the input and there is no tape before the input. This means the linear bounded automata is restricted to this portion of the tape and it would only use that portion of the tape. The emptiness problem for linear bounded automata and the acceptance problem for linear bounded automata can be defined just as we define the acceptance and the emptiness problem for Turing machines. Let us define the acceptance problem for linear bounded automata. ALBA is going to be set of all pairs m, w, where m now is a linear bounded automata that accepts a string w. The question arises, is ALBA decidable? So the acceptance problem for linear bounded automata is as follows. You're given a linear bounded automata and a string, and you have to decide whether this string will be accepted by this linear bounded automata. Well, remember, the acceptance problem for Turing machines was exactly the same, except for instead of a linear bounded automata, you were given a Turing machine. We know that the acceptance problem for Turing machines is undecidable. What about the acceptance problem for linear bounded automata? Well, let's think about this a little bit. A linear bounded automata uses only a fixed portion of the tape that contains the portion that contains the input. So it does not use any extra memory. It does not use any extra portion of the tape. Therefore, its tape head is always restricted to a certain amount, to actually the portion where the input is given. So if the input has length n, then its tape head never moves off those n tape cells on which the input was given to it. Therefore, a linear bounded automata is a much simpler machine than a Turing machine. Well, let's first prove one particular fact about linear bounded automata. So, the theorem that we want to prove is, suppose you're given a linear bounded automata with q states and g tape symbols. Then there are going to be at most q times n times g to the n different configuration of this linear bounded automata m for a tape of length n. What we're saying is, suppose you have a tape of length n. How many different configurations of a linear bounded automata can be there? And the answer is q times n times g to the n. Why is this? Well, let's recall what a configuration is. A configuration is completely defined by the following three things. A, the state of the machine, B, the position of its head, and C, the tape contents. So you have to tell me what state the machine is in, what are the contents of its tape, and you have to tell me which symbol is being scanned by its head. Now, suppose you have a linear bounded automata M which has q states, then for the state there are only q possibilities. There are n possibilities for the position of its head, and there are g possibilities for each cell, and since there are n of them, therefore there are at most g to the n total possibilities of what you can put on the tape. Let's look at an example. Suppose M has 7 states and 5 tape symbols. How many different configurations you can have on a tape of length 3 for this linear bounded automata M? Well, if you think about it, the tape contents, there are only 3 cells, so there cannot be too many configurations. That's what this theorem is saying. There cannot be infinite amount of configurations. It would be finite for this linear bounded automata, and actually we can specify the number of distinct configurations with this simple formula. This particular machine can be in 7 states. So to specify a configuration, you have to tell me a state. There are 7 possibilities of it. Then you have to tell me which cell the tape, the head is scanning. So those are 3 possibilities. So you can give me its tape position by writing down the cell number. And then for the first cell, there can be 5 possible symbols in it. Same for the second and same for the third. So the total number of configurations that this linear bounded automata can have is 7 times 3 times 5 cubed. So let M be a linear bounded automata which has Q states and G tape symbols. Then if M makes more than Q times N times G to the N steps on an input X of length N, then M does not halt on X. Well, what does this theorem say? This theorem says that suppose you run a linear bounded automata M on an input X, and that input X happens to have N symbols. So the length of the input is N. If you run M on this input and it keeps running for a while and you keep counting how many steps it's taking, once it takes more than Q times N times G to the N steps, you can be sure that the machine is never going to halt on this particular input. Well, why is that? We have argued that the number of configurations that a linear bounded automata can have on an input of length, on a tape of length N, is bounded by Q times N times G to the N. Now, if the machine is taking more than these many steps, then it must have repeated one configuration. Since it has a repeated configuration and the machine is a deterministic machine, therefore it is going to keep repeating that configuration and never halt. So on a given input of length N, after simulating M on that input for a finite amount of time, we can be sure that this machine will never halt on this input. Why? Because this machine is a linear bounded automata. We cannot say the same for a Turing machine, because the Turing machine can start using other parts of the tape and it can use more tape. So there's no way to bound after how many steps the machine must repeat itself. On the other hand, for linear bounded automata on an input of length N, after Q times N times G to the N steps, we can be sure that this machine is never going to halt. So this is a theorem that is strictly true for linear bounded automata, but an analogous statement would not be true for Turing machines. Well, how can we use this theorem? We can use this theorem to solve the acceptance problem for linear bounded automata. Let's have a look. We want to prove that a LBA is decidable. The main point is we can simulate an LBA on its given input only for a finite amount of time to decide if it accepts that input or not. Let's look at a decider for ALBA. Let's formally give a decider which decides ALBA. Let L be a decider given by the following description. When it receives an input M, W, where remember M is now a linear bounded automata and W is a string, it calculates N, which is the length of the string. Then it will simulate M on W only for Q times N times G to the N steps, not more than that. If M accepts, then it will accept M, W, otherwise it will reject. By our previous theorem, since M is a linear bounded automata, if it does not accept its input in Q times N times G to the N steps, then it is in an endless loop. The machine will go on running forever and never halt and never accept its input. Therefore, first thing we notice is that this this Turing machine that we have described is a decider. It halts on all inputs because it runs the simulation for a finite amount of time. B is that it's going to accept all pairs m, w where m accepts w. If m accepts w, it does so in less than or equal to q times n times g to the n steps. And therefore, this linear bounded automata accepts exactly the language ALBA. Therefore, ALBA is decidable. The acceptance problem for a linear bounded automata is decidable. The reason we were able to prove this thing, the main point again was a linear bounded automata only uses a fixed portion of the tape for a given input, and therefore if it does not halt in a finite amount of time, which we can calculate, then it never halts. Therefore, we don't have to simulate this linear bounded automata on its input for an infinite amount of time. After q times n times g to the n steps, we can just stop this simulation and say m is not going to accept w. Once again, m here is a linear bounded automata. The same statement is not true for Turing machines. Well, so the acceptance problem for linear bounded automata is easier than the acceptance problem for Turing machines. The acceptance problem for Turing machines is undecidable. On the other hand, the acceptance problem for linear bounded automata is decidable. Well, in this course, we have looked at acceptance problem for many other models of computation. For example, we looked at the acceptance problem for DFAs. We looked at the acceptance problem for linear bounded automata now. We looked at the generation problem for context-free grammars. We looked at the generation problem for regular languages. So let's look at the summary of what we have done so far. Recall that we had the acceptance problem for DFA, where you're given a DFA and a string, and what you want to do is find out if the given DFA will accept a string w. We showed that a DFA is decidable. Why was a DFA decidable? The main reason that a DFA was decidable was because you can simulate the machine D on its input for only n steps. A DFA accepts its input in n steps or not. Therefore, this simulation was finite, and we showed that this problem is decidable problem. Then we looked at a reg, which was the set of all r, w, where r is a regular expression that generates the string w. So in this problem, you're given a regular expression and a string. So you're given a regular expression r and a string w, and you want to ask whether this regular expression r can generate the string w. Well, this problem was decidable. What we did was we took this regular expression r and converted it into an equivalent DFA. And there are algorithms that you have learned in your previous automata course which will allow you to take a regular expression and convert it into a DFA. Once we convert the regular expression into a DFA, we could use the decider for a DFA to decide if the DFA will accept w. And answering that question is the same as answering the question whether the given regular expression generates w. So this way we were able to show that a reg is also decidable. Then what did we do? We looked at this other problem, which was ACFG, where now you're given a context-free grammar G, and you want to know whether, and a string w, and you want to know if the context-free grammar G generates this string w. Once again, we showed that this problem was decidable. The way we did that is we said, well, if I take a context-free grammar, we know algorithms that will convert it into Chomsky normal form. Once we have converted a grammar into Chomsky normal form, then it generates a string of length n. It does so in a finite length derivation. In fact, the length of the derivation does not need to be more than 2n. So what we can do is we can write down all derivations of length less than or equal to 2n and see if our string is generated by one of those derivations. Once again, the number of derivations was finite. For a given string W, we could calculate how many derivations are there and what is the length. And we could enumerate them in a systematic way and see if the string W came up. If it did, then of course G generated W. If it doesn't show up, then we are sure that G can never generate W. And therefore we solved the acceptance problem for context-free grammar. So ACFG was decidable. We can also look at this problem APDA, where you're given a push-down automata P and a string W, and you want to know whether the push-down automata P accepts the string W. Well, is the acceptance problem for push-down automata also decidable? The answer is yes, because you know an algorithm which will convert a non-deterministic push-down automata into equivalence context-free grammar. So all you have to do is take the non-deterministic push-down automata P, convert it into equivalent context-free grammar, and then use the decider for ACFG to find out if G generates W. That answer will tell you if the non-deterministic push-down automata P accepts the string X. We can also look at another problem, and we looked at it, which was called ANFA. This was the acceptance problem for NFA. In this case, you're given a non-deterministic finite automata and a string W. And the question is whether the non-deterministic finite automata N will accept this string W. We showed that the acceptance problem for non-deterministic finite automata is also decidable. How did we do that? Well, we know an algorithm which converts a non-deterministic finite automata into a DFA, into an equivalent DFA. So all we have to do is take the non-deterministic finite automata, convert it into a DFA, and then use the decider for ADFA to find out if the DFA D accepts W. The answer to the question whether D accepts W would be the same as whether N accepts W, since N and D were equivalent machines. N was an NFA and D was a DFA which accepted the same strings. Therefore, all these acceptance problems are decidable. We've now shown that the acceptance problem for linear bounded automata is decidable. Once again, why? Because all you have to do is simulate the linear bounded automata on its input for a finite number of steps, which is q times n times g to the n, and you would know if the linear bounded automata M accepts its input or not. Now, let's look at another question concerning linear bounded automata which is not decidable. So linear bounded automata is a simpler model than Turing machines. We can solve its acceptance problem. However, its emptiness problem is undecidable. So let us define the emptiness problem for linear bounded automata. ELBA is going to be the set of all M such that M is now once again a linear bounded automata and the language of M is empty. So the question we want to ask is ELBA decidable? Is it possible to write down an algorithm which will take as an input a description of a linear bounded automata and tell us whether the language of this linear bounded automata is empty? Let's think about it a little bit. How can we conclude that the language of a linear bounded automata is empty? We have to convince ourselves that this linear bounded automata will not accept any strings. However, there are infinitely many potential inputs to this linear bounded automata. Sigma star is infinite. So if we try to simulate this linear bounded automata on all these strings, that's going to be futile. We will never know the answer. It would become an infinite computation. This gives us an indication that this problem seems difficult, at least on the surface. We can try to think of algorithms, more clever methods, which will allow us to analyze the linear bounded automata and tell whether its language is empty or not. On the other hand, now we can try something else. We can try to show that this problem is undecidable. Since we know now techniques which will allow us to show that problems are undecidable. So somehow what we will do is we will use our previous line of argument. We will say that if ELBA was decidable, then ATM, the halting problem, will be decidable. That would be a contradiction, and we will eventually prove that ELBA is not decidable. We will show once again that if ELBA is decidable, then ATM is also decidable. Well, what would we like to do? Suppose we are given an input m comma w, where m now is a Turing machine and w is a string. We want to construct a LBA B such that B is going to accept only the accepting computation history of m on w. So, given an input m, which is a Turing machine, and w, we would look at the Turing machine m and the string w, and from there construct a linear bounded automata B. This B will only accept accepting computation histories of m on w. Now, if m accepts w, then there is at least one computation history of m on w which is accepting, and therefore the language of B is not going to be empty. On the other hand, if m does not accept w, then there are no accepting computation histories of m on w, and therefore the language of B will be empty. Thus, the emptiness of B will tell us about whether m accepts w. In order for this program to work, we have to understand what a computational history is. So let's look at the concept of computation history. Suppose m is a Turing machine. We have already defined the following concepts. A state of a Turing machine is the current state, and it only tells us about what state the machine is in. A configuration is a much more elaborate thing. It tells us what the state of the Turing machine is and all the tape contents. So, if you give me a configuration of a Turing machine, in principle, from there on, I can tell you how the Turing machine will behave, what is the next step it will take, and the next step, and so on. So, configuration tells me the state and all the tape contents. A computation history is a sequence of configurations. A computation history on input W will consist of configurations C1, C2, all the way up to CL, such that C1 is the initial configuration of M on W, and Ci yields Ci plus 1. So, a computation history gives you an initial configuration, and after that, it gives you the next configuration that the machine has gone into, and the next configuration, and the next configuration, and the next configuration. So, if you think of a configuration as a snapshot of the machine, well, what you're doing is you're taking the snapshot of the machine, running it one step, taking another snapshot, running it one more step, taking another snapshot, and so on and so forth, and you make this whole file. This file is the computation history of the Turing machine on the input W. A computation history tells you exactly what the machine would do if you give it the input W. A computation history can be finite, so you can have L configurations in it, and it tells you what the machine does in the L steps which it performs on the input W. We will say that a computation history is an accepting computation history if the last configuration is an accepting configuration. So, a computation history tells us whether a Turing machine M accepts W. A computation history is a mathematical proof, a way of convincing someone that M, a Turing machine M, will accept a string W, because what you're doing is giving the initial configuration, the next configuration, and so on and so forth, and pointing out that the last configuration is an accepting configuration. So a computation history, an accepting computation history on W is a mathematical proof that M will accept the string W. We will encode a configuration into a string as follows. Suppose C1, C2, C3 all the way up to CL is a computation history. We can encode this computation history by writing the first configuration, putting a hash sign, writing the second configuration, putting a hash sign, and so on and so forth till we write down the last configuration. So we can encode computation histories into strings. Now what we will do is we will define a linear bounded automata which will only accept the computation histories, accepting computation histories of a Turing machine M on W. Suppose you give me a Turing machine M and W, we will construct a linear bounded automata B such that B accepts the accepting computation histories of M on W. Actually, B will accept the encodings of all accepting computation histories of M on W. Let's look at how this linear bounded automata M will look like. Suppose it gets the input C1 followed by a hash sign followed by C2 all the way up to CL. So it gets L configurations. The first thing it'll do is it'll check if the first configuration is the initial configuration of M on W, that is it's Q0 followed by the string W. It will also check if the last configuration has an accept state. Then it will check if Ci yields Ci plus 1. How can a linear bounded automata do that? Well, the transition function of M is going to be hard-coded in this linear bounded automata. It will zigzag between Ci and Ci plus 1 to make sure that Ci yields Ci plus 1. See, if you're given two configuration followed by a hash sign, and if somebody asks you if this configuration yields that configuration, initially you will start matching symbols. And you know that wherever you find a mismatch, that can only happen if the transition function allows it. So this linear bounded automata will zigzag through its input, making sure that this configuration yields the next configuration. Now, why is this machine a linear bounded automata? Notice the input to this linear bounded automata is not W. It's a whole computation history. So suppose the whole computation history of M on W is laid out. And we just have to check if this is an accepting computation history. We will only use that portion of the tape on which the computation history was written on. We will not go beyond that, simply because to check the first configuration, whether it's initial one, we don't need to move off the input portion. To check whether the last configuration is an accepting one, all we have to do is detect an accepting state in the last configuration. And to check if one configuration follows the other, we just have to zigzag the tape head across and never go off the history which was written out for us. So this would be a linear bounded automata. What does this linear bounded automata do? Let M and W be given and B be constructed as we have specified. Then the language of B is going to be empty if M does not accept W, and it's not going to be empty if M accepts W. Why is that the case? Well, B is only accepting computation histories of M on W. So if M does not accept W, no one can ever write an accepting computation history of M on W. There aren't any, and therefore the language of B is empty. On the other hand, if M accepts W, then there is at least one computation history. In fact, since M is a deterministic Turing machine, there is exactly one computation history of M on W which is accepting. And that particular computation history will be accepted by B, and therefore the language of B will not be empty. So what have we been able to do? Given a Turing machine M, W, the question whether M accepts W has been reposed into the question whether the language of B is empty or not. So we have converted the acceptance problem for Turing machines into the emptiness problem for linear bounded automata. Now what we can do is we can argue that the emptiness problem for linear bounded automata is also undecidable. Let's do this formally. The theorem we want to prove is the emptiness problem for linear bounded automata is undecidable. Suppose the contrary. Let us suppose that ELBA is decidable. Then there is a decider R which decides ELBA. Now we consider the following decider S. On input m, w, it constructs the linear bounded automata B that we have described earlier. Remember that the language of B is going to be empty if m does not accept w, and it's going to be not empty if m accepts w. So now decider S can run R on B. If R accepts, that means the language of B is empty, which means m does not accept w, and therefore S can simply reject its input. On the other hand, if R rejects, then the language of B is non-empty, which means m accepts w and it can accept. So S is going to be a decider for ATM, which is a contradiction, and that shows that ELBA is also undecidable. As you can see, the emptiness problem for linear bounded automata is a difficult question. It is undecidable. You cannot make a Turing machine which can analyze a linear bounded automata and tell you whether it accepts the empty language or not. Well, we had also looked at the emptiness problem for DFA, and we said that that problem was decidable. How do we decide that problem? We take a DFA, we minimize it. If you minimize a DFA and that DFA accepted the empty language, then you will end up with a one-state DFA, which is a rejecting state, which does not have any accepting states. So if you minimize the DFA and get this trivial DFA which rejects everything, then you will know that the original DFA was accepting the empty language or not. So the emptiness problem for DFA was decidable. We also saw that the emptiness problem for context-free grammars is decidable. Then we said that the emptiness problem for Turing machines is undecidable, and now we have proved that the emptiness problem for linear bounded automata is undecidable. Let's have a look at the proof that the emptiness problem for context-free grammars is undecidable. Let's recall the proof. We defined the emptiness problem for context-free grammars, ECFG, which was the collection of all grammars G such that they don't generate any strings. We asked the question is if this language is decidable, and the answer was yes. Here is a decider for ECFG. On input G, we mark all the terminals of G, and then we run the following loop while no new symbols are being marked. If we have a production A which goes to x1, x2 all the way up to xn, and all these symbols on the right hand side are marked, then we also mark A. This is a very simple algorithm. Thus, if the start symbol is marked, then it is possible to generate all terminals starting from the start symbol. Therefore, we reject the input, otherwise we accept. So, this simple algorithm or this decider decides the emptiness problem for context-free grammars. Well, is there a problem for context-free grammars which is undecidable? Is there a problem which is so difficult concerning context-free grammars which we cannot decide, for which we cannot make a Turing machine to decide that problem? That would be a very interesting question. Well, there is one. Let's have a look at it. Let's define another problem for context-free grammars which we call all CFG. And this consists of encodings of all grammars G such that G is a context-free grammar and the language of G is all of sigma star. The question is all CFG decidable or not? So, you will be given a grammar G and you have to decide if it's possible to generate all possible strings in sigma star from this grammar, whether this grammar generates all possible strings. How will we approach this problem? Well, I am given a context-free grammar and somehow I have to convince myself or answer the question whether this context-free grammar generates all possible strings. One simple idea that comes to my mind is I take one string, try to generate it from this grammar, then take another string, try to generate it from this grammar, then take a third one, and so on and so forth. However, this idea is futile. It is not going to work. The reason it's not going to work is because there are infinitely many potential strings in sigma star, and this idea will take infinite amount of time, and therefore I'll never be able to answer the question that I'm after. Well, if I really think hard about it, I don't get any other ideas, and therefore I can abandon the strategy of trying to show that this problem is decidable, and I can try to show that this problem is not decidable by showing once again that if I could decide this problem, then I could solve the halting problem. This would be once again a contradiction, and I would have shown that this problem is undecidable. Remember that there are infinitely many potential strings, so it seems that this problem is not decidable. But our goal is not to just say that the problem seems undecidable, but to prove that it is undecidable. So the next theorem we are going to prove is that all CFG is also undecidable. What we will do once again is to show that if there is a decider for all CFG, then we can make a decider for ATM. Since ATM is undecidable, therefore there cannot be a decider for all CFG. So suppose we are given a Turing machine M and a string W. What we want to do is construct a push-down automata D such that D is going to reject the accepting computation history of M on W and accept all other strings. So this push-down automata D is going to only reject the accepting computation history of M on W. Now if M accepts W, there's at least one computation history which is accepting of M on W, and therefore D is not going to accept all strings. It will actually reject this one computation history. On the other hand, if M does not accept W, then D is going to accept all possible strings. Since there are no accepting computation histories of M on W, therefore D will, and D is designed only to reject an accepting computation history, therefore it will accept all strings. Thus, the language of D is going to be sigma star if M does not accept W, and it's not going to be sigma star if M accepts W. Well, how can we describe this PDA D? Let's have a look. Here we will use a trick. Suppose you give me a computation history C1, C2 all the way up to CL. Now I will encode it differently. The first configuration will be written as it is, followed by the hash sign, but the second configuration will be written in reverse. The third one will be written as it is, and the fourth one would be reverse. So in this encoding, we write down the first computation history, put a hash sign, and the second one is written in reverse. Then the third one is written straight, and the fourth one is written in reverse. So now we're encoding a computation history in a slightly different way. Why are we doing this? This would become clear. The idea is, this kind of input is much easier for a PDA to process. Now let's look at the description of this PDA. The PDA will take a computation history encoded as we have said, and it would accept if C1 does not happen to be the initial configuration of M on W. It would also accept if CL is not a final configuration. It will also accept if there is an I such that CI does not yield CI plus 1. So this push-down automata D is just trying to make sure that its input is not accepting computation history of M on W. Let's look at a little more detail. We will hardcode W in D, therefore it can check if the first configuration is not the initial configuration. Similarly, it is very easy for a PDA to check if an accepting state does not occur in the last configuration. On the other hand, how can a PDA D check if CI does not yield CI plus 1? Well, recall that the way we had done our encoding, if CI was written straight, then CI plus 1 was written backwards. And since D is a PDA, it has access to a stack. So as it goes through CI, it can push CI onto the stack. And then when it sees the hash sign, it can pop the elements of CI and start matching them with CI plus 1 and find out if CI yields CI plus 1. It just has to be careful and make sure that the changes that happen between CI and CI plus 1 are not the ones given by the transition function. So D is going to be a non-deterministic pushdown automata. If it finds out that the first configuration is not the initial configuration of M on W, it will accept. If it finds out that the last configuration is not an accepting configuration, it will accept. If it finds out that one of the CIs does not yield the other CI plus 1, it will accept. Therefore, it will only reject an accepting computation history of M on W. Let's see what we have done. Given M and W, we claim that we can construct a PDA such that D rejects accepting computations of M on W. It accepts all other strings. So what we have done is converted the problem of answering whether M accepts W into the problem of whether the language of D is sigma star or not. In fact, given M and W, the PDA-D constructed earlier has the following properties. The language of D is sigma star if M does not accept W. The language of D is not equal to sigma star if M accepts W. Well, now what can we do with this non-deterministic PDA? In your courses, you have learned that non-deterministic PDAs are equivalent to context-free grammars. In fact, if you're given a non-deterministic PDA, there's an algorithm which will convert it into a context-free grammar G. Therefore, we have been able to show that given a Turing machine M and a string W, we can construct a grammar G such that the language of G is equal to sigma star if and only if M does not accept W. Now we are ready to show that all CFG is undecidable. The theorem we want to prove is all CFG is undecidable. Well, if all CFG were decidable, then there would be a decider R such that the language of R will be all CFG. Well, suppose R decides all CFG, then let's consider this new decider S. On input M, W, it will construct the linear bounded automata we have described earlier. Let's call it D. Then it will convert this D into an equivalent context-free grammar G. Now we will run R on G. If R accepts G, then the language of G is sigma star, which means M does not accept W, and therefore we will reject. If R rejects, then the language of G is not equal to sigma star, which means M accepts W, and therefore we will accept. So this Turing machine S is going to be a decider for TM. We know that ATM is undecidable, and therefore we can conclude that all CFG is also undecidable. Well, you will remember when we were looking at questions from context-free grammars in earlier lectures, we had actually encountered this language, all CFG, and we had said that we are not going to give a decider for it now, and later in the course we will prove that this language is undecidable. Well, now we've been able to show that this language is undecidable. We have a bona fide proof that no one can ever write a program that can analyze a context-free grammar which will and decide whether it generates all strings or not. So far, we have been looking at a lot of problems from language theory. Now we will discuss a very different problem called post-correspondence problem. Post-correspondence problem is just a problem which looks like a puzzle. And we will show that this problem, which deals with puzzles, is also undecidable. This problem will have nothing to do with Turing machines, models of computation, and so on and so forth. So when we pose the question, it would seem to have nothing to do with Turing machines. However, we will be able to show that this problem is also undecidable. Let's have a brief look at the post-correspondence problem. The post-correspondence problem, PCP, is a puzzle. We are given a collection of dominoes, each containing 2 strings on each side. A domino looks something like this. This particular domino has A written on the top and AB on the bottom. In PCP, we are given a collection of dominoes. A collection of dominoes will look something like this. The first domino here has B on the top and CA on the bottom. The second domino has A on the top and AB on the bottom. The third domino has CA on the top and A on the bottom. And the last domino has ABC on the top and C on the bottom. Once you give this collection of dominoes, we can make what is called a list. In a list, we allow repetitions. You can place one domino, another one, and you can keep repeating these dominoes to form a list. We call a list a match if when you read the top of each domino, you get a string. If that matches with what you get when you read the bottom of each domino. Let's have an example of a match here. If I read the top symbols, that gives me an ABC, AA, BC. And same is the case when I read the bottom, I get a ABC, AAA, BC. So the post-correspondence problem is the following. You will be given a bunch of dominoes, a collection of dominoes, and the question is, from these collection of dominoes, can I ever get a match? So what we want to do is write a program that would analyze a collection of dominoes and answer yes if there is a match possible and answer no if there is no match possible. In the next lecture, we will show that this problem, which looks very different and very distinct from the problems concerning Turing machines, is also undecidable. I'll see you next time. Thank you and goodbye.